Hello, I'm Katie Amaral, and this is my final project presentation for the Harvard Extension Deep Learning class. This project investigates the use of physiological data collected from wearable medical devices to detect seizures for epilepsy patients. Wearable devices have the potential to greatly improve the lives of epilepsy patients with the ability to detect seizures outside of a clinical setting. This project is based on the CSCI-E89 study, which includes a time series dataset collected with a sensor dot wearable medical device. The full dataset contains over 11,000 hours of wearable data for 125 patients with epilepsy. The data contains EEG recordings that capture electrical activity in the brain, which is the primary signal for detecting neurological electrical storms and is extremely useful for seizure detection. Data engineering involves a significant amount of pre-processing to prepare the data for model training, as well as post-processing required to evaluate the model performance comprehensively. EEG signals are the inputs to the model, and events data are extracted as labels and are classified as either seizure or background events. Matplotlib is used to render the waveform visualization, showing the EEG signal amplitude over time, along with event annotations to highlight the seizure period. Recordings are sampled into segments. There is a significant class imbalance in the dataset since there are many more background events than seizure events. To balance the two classes, the majority class samples are undersampled relative to the number of minority class samples by a factor of 5 based on the study. Generators are used to preload the training and validation data for model training. The ChronoNet model is a convolutional recurrent neural network designed for time series classification. Convolutional layers detect short-term patterns in the time series and can recognize those patterns across different time positions in the signal. Recurrent layers detect longer-term patterns in the data, keeping a running memory of past information. Window-level metrics measure how well the model performs on the individual segments only. Performing well at this stage is an important starting point, but this will not show how well the model will be able to detect seizures within a continuous EEG signal. Most of the window level metrics look acceptable, although sensitivity has a large training and validation gap. Event level metrics will provide additional insight. Custom functions reassemble segments into events and calculate event level metrics at a range of threshold values. Similar to the study, the best threshold also seems to be at 50%. This project metrics generally look similar to the study results with some improvements in AUROC, AUPR, and false alarms, but with a reduction in sensitivity. That concludes my presentation. Thank you so much for watching. Let me know if there are any questions.